Thanks for coming, and today I would like to give a review of week 7's lectures, Basic Distribution Quantities for Actuarial Mathematics. So first, we'll talk about the truncations of random variables. We have the limited loss random variable, which is a smaller one of the random variable x and a constant d. We also have the left censored shifted random variable x minus d plus. So it's used in like options. So it's the larger one of 0 and x minus d. So the summation of the limited random variable plus the left censored shifted random variable is x. We then talked about the percentile of random variables. First, we define the cumulative distribution function, which is known as the CDF. For continuous random variables, the CDF f of x is the integrating from the probability density function small f of x from minus infinity to x. The 100 times p's percentile, where p is a real number in 0 to 1, is eigenvalue pi or p, such that the left limit of the cumulative distribution function f of pi of p is smaller than p, and it is smaller than f of pi of p. Specifically, if the CDF is strictly increasing, then pi of p is well defined for ln p, which means that we only have one value pi of p for every p. We have the Lindenberg central limit theorem, so it's a generalization of the normal central limit theorem. We have identically independent distributive random variables. Each random variable has a mean and has a variance. Those are not necessarily the same. We denote Sk to be the summation of the variances from the random variable 1 to k. We have the condition for the Lindenberg central limit theorem, which states that actually for ln 1, for the summation of the second order moments under real events. Here the real event is xi minus mu I larger than epsilon times s of n. If this is 0 for ln positive real number epsilon as n goes to infinity, then the central limit theorem holds, which states that 1 over Sn times the summation of the shifted random variables xi minus mu I. The distribution of this random variable will converge to the standard normal distribution n of 0 and 1. When we talk about generating functions, we have the moment generating functions m x of z. Here z is a real number. It is defined as the expectation of e to the power z times x. It is for calculating different orders or moments of x. Specifically, we take derivatives of m x of z at z equals to 0, and then we can calculate the different orders or moments for the random variable x. We also have the probability generating function p of z, where px of z, where z is a real number. It is defined as the expectation of z to a power of x. So if random variables xi's are independent, then both the moment generating function and the probability generating function for the summation of those random variables, the summation of xi is the product of the moment generating functions for those random variables, or the product of the probability generating functions for those random variables. For the loss models in the actuarial mathematics, sometimes we may need the tails of distribution, which measures the probability that some rare event could happen. It is 1 minus the CDF. Also, it is integrating the probability density function from d to infinity for the tails of distribution. Two commonly used distributions in actuarial mathematics is a gamma distribution that has this following probability density distribution, probability density function as a Pareto distribution for calculating the loss. Here, x is larger than 0. Thanks for listening to this review.